Okay, so let's now talk about enthalpy. Okay, the stress on the syllable that has the stress when you pronounce this is the second syllable. We say enthalpy, and that makes it easy to distinguish it from the other property that we'll encounter later, which is entropy. So when you say entropy, the stress is on the first syllable. When you say enthalpy, the stress is on the second syllable. And you can see that if you look up the definition of enthalpy. Okay, notice the way it's, see the second syllable is where your stress is when you pronounce it. Okay, enthalpy. All right, so enthalpy. What is enthalpy? Enthalpy is a property of the system. It has a units of energy. Just like internal energy, it's something we invent because we'll find that it is useful for a lot of things that we do. Okay, and the reason for the invention of the concept of enthalpy has to do with the fact that for most cases, for most situations, we're dealing with processes in the lab that are happening at constant pressure, constant external pressure of 1 atmosphere. Okay? So if your system is open to the atmosphere throughout the process, then that means the pressure of your system is constant. It's going to be equal to the external pressure, so your P final will be equal to your P initial. So we want to be able to deal with state functions that are easy to deal with, that will be simple to deal with when we're doing things at constant pressure, because that's the bulk of the kinds of things we do. So let's go back to the first law and see how we can express the first law in terms of enthalpy, okay? And where the concept of enthalpy comes from. Well, delta U, according to the first law, is Q plus W, right? And Q and W at constant pressure would be what? What's the generic definition for W? It's integral of negative P external dV, right? But if your external pressure is constant and it's equal to the pressure, this is P and it's equal to the pressure, you can pull that out of your integral, correct? So this is just negative P. And what's integral of dV from V initial to V final? V final minus V initial, which is just delta V, right? So there's your work right there, negative P delta V. Well, let's rearrange this and write it more fully. So now I have delta U is U final minus U initial. Okay, and I still have my Q here. And instead of writing delta V, I'm going to write it as V final minus V initial. Okay, if we rearrange this equation, put all the final stuff on one side together, and all the initial stuff also together, what do you get? Okay, here's U final minus P final, V final. Here, I move this over to the left side, so that becomes a plus, right? So I put them together. I have U final plus P final, V final on this side. And I'm going to put together all the initial stuff. So U initial, P initial times V initial. Remember, P is the same thing as P final, is the same thing as P initial, right? So I'll put them together and I get this expression right here. I get U final plus P final, V final minus U initial plus P initial, V initial is equal to Q. Okay? So this inspires us to define another state function as AU plus PV. Okay, so the definition of enthalpy is equal to U, internal energy, plus the product of pressure times volume. Okay, so we're just making up a new property. Internal energy plus pressure times volume. You'll notice the units here are consistent. The unit for internal energy is joules, right? What's the unit for pressure and volume? Liter times atmosphere or liter times bar. That's an energy unit. You can convert that to joules, right? So we say then that delta H must be equal to Q at constant pressure. Okay. Now, a shorthand way of writing this is to say that delta H at constant P, so you put P as a subscript, must be equal to Q at constant P. Why is that so important? Because that tells us that even though Q, okay, is not a state function, it's a path function. It depends on what path you take. Since most of the time we're dealing with a constant pressure path, a constant pressure process, we can actually equate Q to a state function. Okay? And what's the nice thing about having state functions? If you're dealing with processes and you want to calculate changes in state functions, you don't have to actually be able to do the process. You can just imagine a series of processes that will take you from your initial state to your final state. If you can figure out how to calculate the change in a state function for each one of those steps, then you can figure out the overall change of your state function. This is the basis for what you learn in your freshman chemistry as Hess's law, where you manipulate different equations. That delta H that you have in your expression, in your thermochemical equation in freshman chemistry, that's the change in enthalpy associated with the reaction. Why is it called the heat of reaction? Because delta H is the amount of heat flow if the process were to happen at constant pressure. Okay, so significance of this new quantity that we define called enthalpy is that for a constant pressure process, the change in this property, this state function enthalpy, is nothing more than the amount of heat flow into the system. And we already know how to measure heat. So that makes it convenient. All right? So one thing you do have to note that we are assuming here, okay, that there's no other type of work besides pressure and volume work that's involved. So the only work we're stating here is pressure volume work. If there was some other type of work that might be involved, then delta H at constant pressure has to be equal to Q plus whatever other work you have. Okay, so you might see a true or false question on an advanced test that says delta H is equal to Q at constant pressure, and you might be surprised to see that the correct answer for that is false. And the reason for that being false is because it's not really just Q. It's Q plus other types of work. But for most cases, we're not going to be dealing with that, so delta H is equal to Q. All right. So let's apply that idea now. The volume of a system. Did I record? I didn't record. Oh, I did. Okay. The volume of a system changes from 40 liters to 20 liters at constant pressure of 2 atmosphere, and 8.406 times 10 to the 4th joules of heat was released. What's our Q? Heat released by the system. Q is positive or negative? Huh? How much? Positive or negative? Heat out of the system. So Q is negative 8.406 times 10 to the 4th joule. What's our W? Minus P delta V, right? Constant external pressure of 2 atmosphere. So minus 2.00 atmosphere times, what's our change in volume? Negative 20, right? So it's 20.0 liters minus 40.0 liters. Let's figure that out later. So this is going to be equal to negative 2.00 atmosphere times negative 20.0 liters. Negative times negative, that's a positive number. 40.0 liters times atmosphere. How much is that in joules? .0 liter times atmosphere, and a joule is a liter atmosphere is how much? 101.325 joules. Okay, So liter atmosphere cancels out. This gives you how much? 40 times 101.325. 4053. So 4053 joules. 3 sig figs, right? So that's 4.05 times 123 times 10 to the third joules, right? So that's going to be 4.05 kilojoules. That's your work. 4.05 kilojoules for what? Do we have enough information to calculate Q now? So we now have a value of positive 4.05 kilojoules. And what would this be in kilojoules? It's going to be negative 84.06 kilojoules, right? Your Q. Let's put everything in kilojoules. So what's our delta U? First law? Q plus W, right? So our Q is negative 84.06 kilojoules plus our W is 4.05 kilojoules. And that gives you how much? How much? Negative 80.0 kilojoules. Okay. What's our delta H? Constant pressure, delta H is just equal to Q. See, it's the easiest one to calculate. It's just equal to Q. Easier than to calculate delta U. You don't have to worry about the PV work. Okay. And most of the time, that's all we're interested in. All right. So, like I said, the significance of enthalpy is that in most experiments, we do it at constant pressure of 1 atmosphere, so it's easy to measure delta H. All you have to do is measure what? Q. Okay? But the nice thing about delta H is H itself is U plus PV. It's a state function plus another state function times another state function, so H itself is a state function. So it's a better quantity to deal with than Q, because Q is, we don't really like to do path functions, because it will depend on what actual path you take. And so if you want to tabulate results, for example, it's going to take a whole bunch of, you kill a lot of trees tabulating all the results for all the possible different paths. Whereas if you just have values for state functions, then you can summarize all of your experimental data into much fewer pages. Okay, so H is a state function. We can imagine any process in terms of a series of processes. Okay, and we'll illustrate that when we get to thermochemistry. All happening at the same constant pressure, and you just add up the H's for each of those steps to get the overall delta H. Okay, so the delta H for the overall process will just be the sum of the delta H for all the steps. All right, so let's illustrate that with a couple of examples here. Isothermal expansion. Okay, we've already shown that for an isothermal expansion of an ideal gas, delta U is equal to 0, right? Let's show now that delta H is equal to 0. Okay. Okay, so remember we said we were able to show that delta U is 0 from the relationship between Cp and Cv. So we can do the same thing for delta H, but a quicker way is just to, like we did for delta U, you can set up your PV diagram, P1, V1, T1, going to P2, V2, T2, and you can set up alternate paths there, and you should be able to see that regardless of what path you take from P1, V1, T1 to P2, V2, T2, your delta H is going to be 0. Okay? Same thing we did for delta U. But here's a quicker way of doing it. You can just say delta H is delta of U plus PV, since that's the definition of H. H is U plus PV. So delta H is the change in U plus PV. All right, so delta H, let's rewrite that. It's U final plus P final, V final, minus U initial plus P initial, V initial. All right. So U final minus U initial, that's what? That's your delta U, right? And P final, V final, minus P initial, V initial, that's your delta PV. Okay, and we've already shown for an ideal gas isothermal process, delta U is 0, right? So what's delta PV? Okay, P final, V final, minus P initial, V initial. Is that 0? Is P final, V final equal to P initial, V initial? Ideal gas, constant T. Yes, right? Boyle's law. P1 V1 equals P2 V2. So delta H would be equal to 0. All right. So just like for delta U, you can show delta H is 0 for an isothermal process. In fact, you can also show, ultimately, if you play with it, you can show that delta H would just be equal to Cp times delta T. What that is saying is for an ideal gas, your enthalpy is a function of temperature only. Just like internal energy depends only on temperature for an ideal gas. I'm going to keep reminding you, we're dealing with ideal gases here. This is not going to be true for general cases, okay? So we're just dealing with an ideal gas for now. Okay. What about a reversible isothermal expansion of an ideal gas? What's your delta H? Answer. Isothermal, ideal gas, delta H is 0. But if it's irreversible against a constant external pressure, what's delta H? It's still isothermal. It's still 0. What's delta U? 0. Okay. Now, for any gas changing from P1, V1, T1, as I mentioned earlier, to P2, V2, T2, you can show that delta H is just equal to Cp times T2 minus T1, or Cp times delta T. Okay? And here's a quick way of doing that. You can do that using those diagrams that we did last time for internal energy. You can show that delta U, we show that delta U is Cv delta T, right? Regardless of what path you take. Well, you can also show that delta H is equal to Cp times delta T, regardless of what path you take for ideal gases. Here's a quicker way of proving it. This one right here. So delta H is delta of U plus PV, right? So that's delta U plus delta PV. Well, what do we know about delta U? We've already shown delta U is just going to be equal to Cv delta T, right? What's delta PV for an ideal gas? That's P final, V final minus P initial, V initial, right? But that's the same thing as nRT final minus nRT initial, correct? PV equals nRT. So that's just equal to nR T final minus T initial. That's a change in nRT, which is just a change, which is just N times R times the change in temperature. So that's nR delta T. What can we do at this point? Let's simplify that. What do we know about? We can factor out delta T, right? So if you factor out delta T, you have Cv plus nR. What is Cv plus nR? for an ideal gas? That's Cp. And we just proved that's delta H. Regardless of what path you take, if you go from P1, B1, T1 to P2, V2, T2, dealing with an ideal gas, delta H will just be Cp times delta T. Here's another way of looking at it on a PV diagram. Okay. So let's say you have P1, V1, T1 here. Okay. And let's pick P2, V2, T2 over here. You can pick any point you want. The idea here is this. You go isobaric first. Okay. So Q for this, okay, delta H for this is equal to Q, right? Constant pressure, delta H is equal to Q, and Q is just Cp times delta T. And then once you go from that intermediate point, you can now go isothermal towards your final point. What is delta H for this? 0. Isothermal, delta H is 0. And that is why delta H is just always going to be equal to Cp times delta T for an ideal gas. Okay? So that's enthalpy.